then you just unmute.
Pardon?
Can you unmute everyone from the end? Then you just unmute when you have a question.
Oh, okay. Okay, so what was I? Hexagonal. I said you look at the rightful shape of the hexagonal. And the monoclinic. And the base-centered monoclinic also on the bases, we have two additional ones, so meaning 8 in the corners plus 10. And we have the triclinic. The end here also has how many? 8 also. Anyway, our focus will be the structures that are common with the metals, which are the body-centered cubic and the face-centered cubic. Someone's mic is on, but I can't figure out who it is. Please kindly switch off. Okay, so this is just a further illustration of the sides, which sides are equal and which angles are equal. So for the cubic, the simplest form, I'll start here. We know that in a cube, all sides are equal length, isn't it? So A is equal to B. A is equal to B. Look at where my cursor is here. A is equal to B and equal to C. So all sides are equal. And the angles here are also equal. They're all 90. Alpha, beta, gamma are equal to 90. Tetragonal, A is equal to B. So meaning A is equal to B, but C is longer. That's the difference with the tetragonal shape. Okay, so A is equal to B, but not equal to C. However, alpha, beta, and gamma, these angles here are all at 90. Orthorhombic, A is not equal to B, which is not equal to C. However, the angles there are all right angles. They're all 90 degrees. Hexagonal there, A is equal to B, but not equal to C. A is equal to B, which is at 90, but gamma will be 60. Okay. The rhombohedral also has its own properties and so on and so forth. So you look at these one in your own time when I send you the presentation. So metallic crystal structures, they tend to be densely packed, we know that. And the reason for dense packing is typically that one element is present, so all atomic radii are the same. With a metal, when you say copper, you just basically mean that all the atoms there are copper atoms, isn't it? So it means that they all have the same radius. All the atoms have the same radius. Therefore, so it's easy for them to quickly pack up without leaving any space around, some space around. And one thing we know about metallic bonding is that it's not directional. And the nearest neighbor distances tend to be small in order to lower bonds because of lower bond energy. So the neighbor distances tend to be smaller. And then what else do we know? The electron cloud, it shields cores from each other. Electron cloud, remember we talked about the electron cloud, we said in metals, what happens to the electrons in the outer shells? They simply form a sea of electrons, or what is known as an electron cloud. So this one shields the cores from each other. The cores are basically the remaining part of the atom. And they have the simplest crystal structure. So we'll examine both structures, FCC, BCC, and HCP. Okay, of course, the simplest is simple cubic. But the common ones that we'll use usually are the FCC and the BCC. So when I mention a metal, for example, aluminium, you should be able to tell whether it's just by the mention, if you know already whether it's a BCC, body-centered crystal structure, or it's an FCC face-centered, meaning it has additional atoms on its face. Body-centered means there's only one atom at the middle, at the center. So for aluminium, for example, this table here, it's also found in your Callister book, your recommended literature, there's Callister textbook there. So aluminium is face-centered. Okay, it has a face-centered crystal structure, face-centered cubic crystal structure. Cadmium is HCP, chromium is BCC, HCP is hexagonal, closely packed crystal structure. Chromium is BCC, body-centered cubic crystal structure. Cobalt is HCP, copper is FCC, gold is FCC, and you have the radii there, the radii of each atom there, put in nanometers. So aluminium, the radius of aluminium atoms is 0.143 nanometers, okay? Then you have more molybdenum here, for example, is BCC, and you have the radius. So why are you being given this? Because in our calculations, okay, we're going to be using the atomic radius here, and then knowing the crystal structure will help us determine which formula to use, because there are formulas, there are certain numbers or units that are, there are certain figures that are placed for that are used for BCC, that are used for FCC, and so on and so forth. So like I said, nanometer is equal to 10 to the power -9 meters. Take note of that. So the simple cubic structure, this is how it looks like in 3D, very beautiful. So you have, this one is rare. It's a rare structure. It's rare to find atoms that have, it's rare to find elements that are arranged in this structure, the simple structure where you just have the eight atoms, the unit cell, just in the corners, and that's it. Usually you have FCC in the middle there, or, BCC in the middle, or FCC where you have in the side, in the faces there, atoms packed. So this one is rare, and only one element has this structure, and that is polonium. I don't know if you've heard of it before. If you follow the case of the poisoning of some Russian spy by the Russians in the UK, remember that man that was always shown hairless? It's a radioactive element. So it's a quick poison. It's a slow poison, actually. It will kill you slowly. You actually see yourself die. It's quite dangerous. So that is one element that has this structure. So this is our cube. So you see here, this is the simple cube structure, but joined together. So you have one cube there connecting to the other cube. Okay, so you have the bottom layer here, okay, and then you have the top layer. So remember what I said. Let's pick the red one, for example. I said earlier on, I said, for example, this atom is sharing, it's present in how many lattices, or in how many unit cells? In 8. So there's the bottom 4 and the top 4. So meaning each unit cell has 1/8. Okay, 1/8 of the atom. There's a share that they're doing, because there are 8 of them, so it's an equal share. So 1/8. So the coordination number for the simple cubic structure is 6. We'll look at the calculation further. The atomic packing, there's also what is known as the atomic packing factor, the APF. This is the formula there. It's a volume of atoms in the unit cell over the volume of the unit cell. So it's important for you to know the volume of the atoms in the unit cell. And what we're using are just simple formulas that are found in geometry. But you just need to understand where they're coming from. So here is an example here. So you have an illustration here. You have this is your simple cubic structure. So this is your simple cubic structure. Okay, the answer is 0.52. So where are we getting the 0.52? What's the understanding here? So this is your A. This is the distance, isn't it? Your A here. And then we say that it contains how many? 8 times 1/. So there are 8 atoms, isn't it? So 8 of them multiplied by 1/8. So we said each corner is 1/8, isn't it? So if each corner is 1/8 and there are 8 corners, for you to find the amount of atoms inside this cube or inside this unit cell, it means you're going to multiply 8 times 1/8. 8 times 1/8 gives you what?
1.
Gives you 1. So you have 1 atom per unit cell. I hope we're together. So meaning in a simple cubic structure, the number of atoms inside is 1. So you bring this one here, okay? Then what's the formula for volume of a sphere? Since we say that these atoms are what? Are spherical in shape. So meaning for us to know the volume, it means we have to use the formula for the volume of a sphere, which is given here, okay? 4/3 pi times 0.5a. Where is the 0.5a coming from? This is supposed to be the radius of the atom, isn't it? So it's supposed to be 4/3 pi r cubed. That's the formula. So for us to know the r, we're not given, for example, in this case, huh? But then what do we know? We know a, okay? We know a, and remember from our earlier examples, we say that, from our earlier assumptions, we say that it is assumed that these, the atoms are touching each other, isn't it? That was the other assumption. The other assumption was that the atoms are all touching each other. The ones that are neighbors, the neighboring atoms are all touching each other, which means that all the atoms in the corners there are touching each other, as you can see. I hope you're able to see it from here. They are touching each other. So this corner atom, you see the shape here, it's touching this other corner atom, they're touching there. So if they are touching, if this one is touching this one, meaning the radius is up to here, isn't it? Which is half of A. If A is this part and these two are touching, meaning they're meeting halfway, which is 0.5A. So meaning the radius is 0.5A. Are we together there? I need to make sure that everyone has gotten the concept here. Feel free, please, to ask. Okay, I'll assume that everyone, it's either everyone knows what's going on or no one knows what's going on. I'll go with the first one. Okay, so you fit it in our formula. This is a formula. Remember what I said, volume of a sphere is 4/3 pi r cubed. So you have our r there. We figured it out. We brought it to the formula. We brought it to the formula, isn't it? And then here it says volume of unit cell. Volume of unit cell. What is a unit cell in this case here? It's a what? It's a cube, okay. The unit cell here is, remember the top part is volume of atoms. That's why we are calculating the radius of the atom. But the denominator says volume of the unit cell. So meaning we are getting the volume of this whole thing, not just the atoms, but this whole volume inside, the inside part of this whole thing, you need to know it. And that is known as the volume, that's the volume of the cube itself. And what is the volume of the cube from geometry? What is cube volume? It will simply be A cubed, or as we used to like calling it, what was it? H cubed. H cubed, I think, from geometry.
Yeah, H cubed, yes.
Yeah, so in this
H
case,
cubed.
our H is simply depicted as A. It's still the height of the cube. So in this case, we're just calling it A. So it will just simply be A cubed, nothing changes. Okay. So the same A here and the same A being made here. Do we see something? So are we able to find the formula? I mean, are we able to calculate for it?
Yes, yes.
Yeah, so what do we do to find the APF? How do we find the APF? In order to find the APF, we simply make A the subject of the formula, isn't it? That's the only unknown that we have in that formula. We know 1 here, 4/3 pi, we know already, isn't it? 0.5 is known. So the only thing that is not known is A here and the A here. So we simply make A the subject of the formula, and the answer that will give us is 0.52. So you can calculate that for yourself just to prove that that's the correct answer. Are we together?
Oh, Doc, can we go through together to find A?
In order to find A,
Yes.
to solve for A.
Yes.
So you have your pi multiplied by 4/3. I hope we all have our calculators nearby. It's a class, remember. So you need to have your pens, your pencils, your book, and your calculators close by. Want to be like my full-time students who come with popcorn to the lecture, thinking it's a movie. So you come with everything, make sure that you have your learning materials close by. Okay, so what's pi?
22/7.
Hmm?
22/7.
22/7.
Yeah.
So multiplied by 1, which will give the same, isn't it? So you have your 3.1428 on the numerator there. I hope everyone, are we together? Bring your A cubed on the left. Has anyone tried to solve for it? Okay, so if this is ARA here, isn't it? Let's come to where this is. This is ARA. So according to geometry, for us to find A, we have to draw, when you draw a line here, remember the, what is it called? The Pythagoras theorem? Those that still remember that.
Nice.
Remember the Pythagoras theorem? So in the Pythagoras theorem, you had this part, isn't it? The right angle there, and then you have a diagonal here. Okay. So if you have a diagonal coming here, from this corner to this corner, isn't it? So you form a right angle here. So you use the Pythagoras theorem to solve for A. So in this case, you have square three, the square root of 3 times A which will give you just 1 second. Sorry, I think I was giving you the one for the body center. This is simple cubic. So for simple cubic, it's simply A3, isn't it? That's the volume, isn't it? Then the volume of the atoms, when you draw that line, it means it's touching how many atoms? 2 of them. And not 3, like I earlier said. I hope I'm not even confusing you more. But coming to the Pythagoras theorem, if you've got an idea what you need to do there, in terms of when you solve using the Pythagoras theorem, has anyone attempted to do so? The silence. Has anyone managed to solve for A? Okay, let's move forward. We'll come back to it. I suggest to move forward. We'll come back to it. So with body-centered cubic, like I said earlier, we have your atom there in the middle. Okay, so the atoms touch each other along cube diagonals within a unit cell. So along these cube diagonals within, from this corner to this corner, it means that throughout, the atoms are touching each other. Okay, from this corner, I hope you're able to see. From this corner down, if you draw a line from this corner inside through the body atom up to this side. So you find that the line is cutting across atoms. There's no place where the line is cutting where there's an open space like here. Are we together? There's no open space like this open space here. That is what is happening with your body centered, unlike our earlier one. Our earlier one, as you see, if you drew a diagonal from there to there, there may be some space here in the middle. You see, because there's a void. There's a void somewhere around the middle there. So that's the uniqueness that the body-centered cubic structure has. However, not all the atoms can be identical. The center atom is shaded differently. That is only for ease of viewing. So meaning all atoms are identical here, sorry. So the atoms here are identical. So this one is only shaded differently so that you're able to see closely. But in reality, actually, sometimes you find that atoms from a different element will come and fuse themselves here. Then anyway, we have this one for our example. The atoms here are all the same. They're all from the same element. The coordination number is 2. So how many, when the coordination number is simply the number of atoms that are found in this unit cell. So in this case, we have how many atoms? Remember we calculated earlier. So we have one whole atom inside, isn't it? When we're asked to calculate for the number, the volume of the number of the atoms in this particular unit cell, the body centered. So we have one atom, a whole atom, isn't it, in the center, plus in the 8 corners, just like before, isn't it? In all 8 corners, we have 1/8 of atoms. So 1 plus 8 times 1/8. That gives you how many atoms?
Two.
It
Two
gives us
atoms.
2 atoms, yes. 1 plus 1 simply gives us 2. Examples of such elements with such atoms, we have chromium there, molybdenum, tantalum, iron, alpha. Those are the type of elements that have this type of structure and examples. Of course, there are many more, but this is just an example. So for the atomic packing structure for the BCC, and I hope this one gives a better illustration. So you have one in the center, okay? And the ones in the corners, the 8 corners there. So our atomic packing factor comes here. The formula comes back. So the number of atoms in the unit cell we said is how many? It's 2, isn't it? 2. Then the volume of the atom, that's the formula, just like before, over volume of the unit cell. Volume of the unit cell is, it's a cube. So this is the formula for the volume of a cube. A cube, we have our A here. So A can be here, can be here. We say that in a cube, all the sides are equal. Then for the close packed directions, you have your length, which is equal to 4r, which is cubed of 4a. So where is this coming from? It's coming from the Pythagoras theorem understanding also. So we say that inside, when you run a diagonal from this point, okay, through the body-centered atom to this corner, we say that this is how it will look. There's no void, isn't it? There's no void space that you will come across. So using the Pythagoras theorem, this will be A, this will be square root of 3 times A, and this is the square root of 2 times A. So for us to pick, so this is how now, so this is how we calculate now for A. A is simply that direction divided by 4 from this formula. You put A on the left side. Maybe try and do that together again. Let's see if we achieve this one. Then we'll go to the earlier one. So do you understand where the 4r is coming from?
R.
Do we understand where the 4r is coming from? No. Okay, so let's look at this diagonal again. I said diagonal from where? From this point, isn't it? When you run it inside to this other end. So meaning you find what your aim actually when finding diagonals is to find a diagonal such that when you run it, it's not going to run through a void. Okay. it's going to have atoms in it throughout. And the best one is this one, the one running from this end to the other end, because it gives us the arrangement of these atoms like this. So you have, this is our arrow, it's up to here. So you have one arrow here. Okay, that's radius. Plus another arrow here, isn't it? Up to the center. And another one here, and another one there. So you have one arrow, two arrow, three arrow, and four arrow. Is it clear now?
Yes.
Okay, so we agree that four arrows are giving us this side, isn't it? That has this formula, according to the Pythagoras theorem, okay? So length here is 4 arrow, which is equal to this one here. It's here. So now, what you want to do is put A on one side. You're solving for A. So if you solve for A, what do you have on the other side? What remains? Oh, sorry, you're not solving for A, you're solving for R. Sorry, you're finding the radius because the formula here is R, not A, sorry. The radius, the formula is R. Okay, R cubed, isn't it? So what are you solving here for? You're solving for R. So how, what, when you solve for R, when you leave R this side, what happens on this side? You simply have what's here already, isn't it? Divided by this 4. You're simply going to divide this other side by 4. And this is what you get here.
Okay.
Mhm. And this is also what you get here. So for the body centered cubic structure, the packing factor there is 0.68. So what you do here is you remove your A from this situation here, and you have a cube so that it cancels, okay? So you need to remove your A here, and when it comes out of this, when you put it next here, it also have a cube formula, even to have to be to the power cube, the power 3, sorry, to be cubed. So when you remove your A here to be cubed, and you have your A cubed here, when you cancel those, okay, you have canceled out your A. Then what is left for you to do is just calculate for the remaining values in your formula. Or what you can do, or the other one is, how else can you do this? If this is your A, right, you solve for your A. This A here, that's the simplest way to do it. So when you found your R here, sorry. When you found your R here, you come and place it here. At on the denominator. So you have, okay, let me, I wish we had a board. It's a bit difficult to calculate the manner that I'm trying to. So 2 times 4 is 8, isn't it? So you have 8 over 3 on in your numerator, isn't it? 2 times 8 divided by 3. So it's basically 8 over 3 multiplied by pi. And you have the rest there, which is fixing your R cube. And your denominator there, what do you place? You have your your 4 over 3 cubed to the power 3 in brackets. So the final answer should be 0.68. Anyway, so you're going to go through these particular ones. I think at the end we'll try and, or alternatively, I can just calculate some on a piece of paper so that we go through them step by step. Because I think maybe leaving them for you to calculate like this. Maybe if we can, I can just be showing you each step how it's calculated up to the end. Maybe that will be clearer for you. But if for those who have already understood as it is, then well and good. However, the answer there should be 0.68. That is the APF. So let's look at a comparison. For the simple cubic structure, the atomic packing factor is 0.52. For the body-centered cubic structure, we say that the atomic packing structure is 0.68. So we have 0.52 for the simple structure, 0.52, and then we have 0.68 for the BCC. So which one do you think is more closely packed? Simple structure or the body-centered cubic?
Body-centered.
Body-centered is more packed, isn't it?
Yes.
Yes, no wonder the figure is higher than the simple packed one. So that also will help us know as we go on that particular property of metals, the packing of metals, of atoms in a metal. It will help us know which metals easily diffuse and which ones don't easily diffuse. So the ones that are most likely to, diffusion is most readily going to happen, diffusion, isn't it? It's most readily going to happen where there's space, where your unit cells or your lattices have space to accommodate other atoms from other elements, for example, isn't it, in a mixture where you're having diffusion happening.